Okay, so hello everyone, and welcome to our Virtual Dynamics webinar. As you know, the first release of 2026 was made available, so we are here sharing with you what's new in Virtual Dynamics. My name is Adrian Mihalchoiu. I'm head of customer training at Enhorise France and will be the moderator of this session presented by Swapnil Shah, Virtual Dynamics product manager, with a live demonstration by Prashant Mane, application engineer. Uh, you know him well. Swapnil Shah is the product manager for Virtual Dynamics and the first point of contact for anything related to it, whether technical, commercial, or administrative. He is equally comfortable switching between engineering details and business decision, and he genuinely enjoys being involved in all of it. His perspective comes from 14 years of working with Virtual Dynamics in different roles. He started as a user, moved into development, and now leads the product from a commercial and strategic standpoint. That full circle journey gives him a practical understanding of both what users need and how the product evolves behind the scenes. Prashant has over 13 years of experience in multi-body dynamics simulation and has been a dedicated Virtual Dynamics user for the last 11 years. His experience combines hands-on simulation work with technical consulting and customer-facing application support, giving him a strong perspective on both product capabilities and user expectations. He now supports customers globally in adopting and applying Virtual Dynamics effectively across different engineering use cases. So we'll start with a quick walkthrough of what's new in the latest release, just enough to give you a sense of where things have evolved. After that, we'll move straight into a live demo and spend some time exploring the features in more detail. Towards the end, we'll switch to an open Q&A. Feel free to drop your questions in the dedicated Teams panel at any point during the session, and we'll pick them up as we go and address them live. With Swapnil and Prashant with us today, we should be able to cover a wide range of topics and keep the discussion interactive. Thank you all again for attending this webinar today, and thank you, Swapnil, for giving everyone here a chance to learn more about the newest features Virtual Dynamics brings. Swapnil, to you.
Thank you for the introduction, Adrian. And from my side, I am delighted to welcome everyone for the webinar today. It's called Virtual Dynamics 2025.2, but it is the first new release of the year 2026. There are many new features that I would like to demonstrate today, and I also look forward to an engaging session through your questions. Starting with an overview of the new features. There is a brand new look and feel to the software with a new light and dark themes. A geometrical solution of a dock clutch was introduced a few releases ago. Now this has been further extended with an analytical gear synchronizer for easy gear shifting simulations. Another completely new UDE or user-defined element, which is coined as mass balancer, is available now to remove any unrealistic rotational imbalance in the system. Along with that, we have also been working on improving the post-processing, analyzing, and 3D visualization capabilities by extending, for example, in this case, the bearing pressure animation to all the hydrodynamic bearings. In the same vein, we also introduce now a 3D visualization of the gear contact behavior. Along with all of that, we have also improved our licensing for stability, security, as well as usability. That is not all. We have been quite busy. There are a long list of improvements, bug fixes, enhancements. Even with smaller fonts, I cannot fit everything into a slide. So I have just taken out the most important ones. So I invite all of you to explore our release notes for more information. And now to go into the little details, let me start with the most obvious change, the light and dark themes. As they say, the first impression of a software begins even before the first click. Yeah. And keeping that in mind, we now bring to you a modernized user interface with improved usability and hopefully better visual clarity. So now you have the ability to toggle the application appearance between this light or dark interface configurations, which provides a modern and cleaner look. Also, this new color palette, it comes with completely redesigning of the icons and the dialog boxes. And one of the effects is that it gives now cleaner plots and icons. The edge rendering is sharper, and along with that, for controlling the model, the graphical interface, now it is also possible a more CAD like CAD like system, or some preprocessors that you might know, a complete control via the mouse. You do not necessarily need to press R, T, S, and all the different shortcuts. So this is a visual cleanup, but I'm pretty sure in the last few weeks I have been very excited from it, and a lot of regular users I think will appreciate these changes and welcome the new look. Going to one of the brand new elements, the gear synchronizer. So the behavior of a gearbox, of a manual gearbox especially, of the system, is not only about selecting the gear, but also about synchronizing the speeds and defining the dynamics of the engagement during the gear change. So in this new gear synchronizer UDE, defined element, this is handled now by an analytical solution allowing detailed dynamic modeling of both the phases of the gear shift. I will go into the phases shortly, but what this aims for is enabling the simulation of different gear engagement conditions during coupling as well as decoupling phases. Yeah. So the two phases which I mentioned. So first you have the possibility of defining a friction clutch, right, which will reduce the speed delta between the shaft and the gear using a torque buildup. And once the speed delta has reduced below a particular threshold, which the user can define, the dog clutch would engage for a fit coupling of the shaft and the gear, right? The dynamic behavior of this entire engagement or a disengagement process, uh, like including timing effects, delays in the system, different ramp characteristics of how fast you engage or disengage, all of this can now be accurately modeled using intuitive parameters. The dog clutch part itself is modeled as a torsion spring damper system. And once it is engaged, of course, it becomes the primary path for torque transmission, because of course you do not have relative speed in the friction clutch. It also additionally introduces, let's say, a realistic stiffness and damping behavior into the gearbox, which, sometimes if you are just using a fixed joint between the gear and the shaft, then this additional stiffness damping through the synchronizer mesh may be missing in the model. With the brand new UDE, we are also introducing a reference model in the shared library, along with a step-by-step, the self-guided tutorial to help users get started quickly. Moving on to yet another brand new feature, which is coined mass balancer. So in dynamics, many important rotating components, in reality, they undergo an additional balancing in the manufacturing line, right? To account for any imbalances caused due to tolerances or wear in the, in the tools during production. Truthfully, our ideal CADs, which we work with, generally don't suffer such issues, but there are also exceptions for that. But additionally, it has been experienced regularly that the discretization which we do, right, when we create the FE mesh of the complex geometries and the curves, sometimes it introduces artificial and sometimes very unrealistic imbalance in the system. And in a highly loaded and dynamic system, this can actually lead to noticeable excitations and loads. This was a trap which we actually noticed many users falling into, unknowingly having imbalanced system. I have personally seen an extreme case of for example, a 6-cylinder crank train displaying and very unexpected 2.5 order excitation due to this kind of imbalance in the system, right? So what this feature does is lets you automatically balance all your critical rotating components with a few mouse clicks actually. And here too, I must add that a step-by-step self-guided tutorial to introduce all the users to the workflow, along with many helpful tips of how to prepare the model if you want to do this kind of balancing, has been created. Along with the themes, there are even more animation and visualization improvements, as I mentioned earlier. And at first, let us look at the bearing pressure animation. If you're like me, if you're working with hydrodynamic bearings of any kind, then the bearing pressure animation feature has, for me, always been a very useful tool to visualize the oil film pressure directly on the bearing surfaces like this. Yeah. And one approach, for example, which I often recommend is having a split screen view with animation on one side, the 2D plots on the other side, which helps build a much clearer mental picture of the behavior and easier to interpret. If you are not using it, not familiar to it, I would definitely recommend it because it simplifies the understanding and imagination of the local loading conditions and the dynamic behavior. What is new here is that this capability is no longer limited to crankshaft bearings and supports the hydrodynamic bearings, rigid or flexible, 2D or 3D of all kinds. And again, it is no longer limited only to the crankshaft main and pin bearings, which means the piston pin bearing in your timing drive, valve train, counterweights. It can be used for any broader application. Another, I would say, also much requested and maybe required improvement in the analysis capability is in the 3D gear contact visualization. So honestly, this has been developed based on many customers' requests and inputs, and I'm sure some of you are logged in today just to see this particular improvement. It honestly doesn't need much emphasis uh, to say how important tooth contact dynamics and the contact position along the flanks when evaluating the gear behavior is, right? So now for 3D gears, whether you are working with internal geometry, external geometry, I mean importing a CAD or flexible bodies, it is now possible to visualize the contact pressure distribution directly on the gear pair. Yeah. Along with providing deeper insights, one of the side benefits which I noticed from this is looking at such an animation help me clearly assess, whether the selected surface resolution of my 3D gear is appropriate, whether it's too fine or too coarse, for example. And in a very similar improvement, the wear improvement, the wear indicator, which is the product of the contact pressure and the sliding velocity, can also now be visualized in a 3D animation, which means you can put this animation, you can put the rolling velocity or the contact pressures on the other side of the plot and compare them with each other. And this, of course, is an indicator for wear potential as well as local hit generation, and can become an important tool for wear analysis or thermal assessment of the flank geometry, especially if you are doing microgeometry improvements. We have in our test cases seen significant changes with minimal microns of change in the microgeometry. And last but not the least, so we have been always updating our license and infrastructure. And in this case, we have made a significant change to improve the configurability, usability of the license manager, going to a very recent version of the LMX licensing, making it web-based. It's no longer dependent on Java, and it's YAML based or JSON based configuration. So of course, much more easier for, let's say, people to interpret. That was a very quick overview of the major improvements with this release. And with that, once again, I would remind you, if you have any questions, you can already start asking them via our Q&A box. And I hand over the screen and the words to Prashant, who will do a live demonstration of the features which we just discussed. Over to you, Prashant.
Thank you, Swapnil. Thanks for the introduction and for setting up today's demonstration. So Swapnil has set up the stage for us where he has introduced us what is in the new version. But now I will go through how it can be useful for you. So I will bring up the virtual dynamics session. As Swapnil mentioned during his presentation, that now we have cleaner visuals. So you can see the wireframe mode, the shaded mode. The rendering is much more better. The dialog box here, you can see we have improved readability. Even the icons are now also updated with modern look to it. Similar to the icons and color packs in the settings menu, we now see the option for theme. Here, the user can select between the light mode and the dark mode based on his preference, whether you prefer a bright daytime feel or you want a calm nighttime look. Over the period, what I have used, my personal favorite still remains the light mode. So I will switch back to light mode for the further activities. Now the feel for this tool looks really good. However, it took lot of improvement. This took lot of efforts from our developer to make our day-to-day work more comfortable. So that was about improving the overall user experience. Next, we move into something more functional. Since right now we have the transmission model already open, let's use this setup to understand how gear shifting actually happens. Over here, this is a 2-speed manual transmission. The bottom shaft over here is the input. The dyno provides the input to that input shaft. On the left, we have the gear pair 1 with a speed ratio of around 2. On the right, we have a gear pair 2 with a speed ratio of around 1.5. In this model, we have introduced extra resistance by increasing the shaft inertia. This just acts as a simplified representation of the resistance that usually come from other vehicle parameters. During shifting, the engagement cannot happen instantaneously because the rotating components must align first. Virtual dynamics now can analyze this synchronization more realistically. Think this as a two-stage process wherein the friction clutch brings the rotational speed closer together for the two rotating components. Later, the dog clutch completes engagement and transfers the final torque. Inside the setup, we now define how the synchronization behaves. Pressing function F1 opens the help documentation where you can find detailed information about how you can model the gear synchronizer in virtual dynamics. In this model, the user can define the gear synchronizer signal in different ways, either directly from a solver variable or through a communicator, or he can use his own custom function for analysis. We now run a generic analysis simulation to further understand how the synchronization happens. Since it will not take much of time, I will run a quick interactive run over here. So based on your processor and graphics card, this takes some time. This time it is taking some more time than I expected, but now the simulation is complete. So we can move to the post-processor part. So right now I am looking for the first synchronizer signals, and we plot the synchronizer signal and the angular velocity delta plots. So over here, this plot shows how the transmission performs a smooth gear change. The green line shows the gear shift command, what we had given in the example. The blue line shows the speed delta between the two rotating components. At the beginning, the delta is high, meaning both the sides are rotating at different speeds. So the engagement is not ready yet. Once the synchronizer is activated, it starts reducing the speed, and you can see that the blue line is moving closer to zero. When the speed difference becomes small enough, the gear can change smoothly without any shock. Then we command the next gear stage and the process repeats to settle at a new operating condition. So here you can see the speed ratio has been, the delta has been changed from this level to the new gear pair ratio level. We can also have a look at how the torques are transferred between these mechanisms. This plot shows how the torque is transferred. The blue line is the friction clutch torque. This is the synchronizer working to match the speeds between the rotating parts. The green line is the dog clutch torque. This represents the final mechanical lock, as Swapnil mentioned that it is a spring damper element, which finally transmits the drive after synchronization is complete. At the beginning, both the torques are almost zero because no gear engagement is happening. Let us focus on the gear engagement 1. Around 1100 milliseconds, the friction clutch torque rises sharply. This means the synchronizer starts working and generates torque to reduce the speed difference. At the middle, we can see that the synchronizer briefly works harder to overcome the extra resistance we had added and to maintain the synchronization. Once the speeds are matched, the friction clutch hands over the load. Then the dog clutch torque increases and stays steady. This means the gear is fully engaged and the torque is now transmitted through the mechanical connection rather than the friction. Finally, when the shift ends, the torque returns. That gives us more realistic representation of shifting behavior. Now, another area where the realism matters is the rotating system, which brings us to our next feature, the mass balancer. A mass balancer uses 4 small points to remove the imbalance from another rotating component. Imbalance can happen because of manufacturing tolerances we have, or also can arise due to the approximation errors from FE discretization. Thus, this can be very useful in components like crankshaft in ICE setup or rotors, what we have in motor generators. Right now, I have opened an example in a standard interface where I had already created mass balancers in the template mode using predefined locations. The mass balancer is the part of base components because it can be applied to any rotating components across crank train, wall train, motor generator. So no different licensing is required for this module. Here you can see the 4 mass points are attached to the flexible component. It is important for while preparing the flexible component that there are 4 suitable interface nodes or RB elements available. These elements serve as the connection points for applying the balancing masses to the flexible body. When I say calculate mass, you will observe the mass data being updated. And a report is generated. So the mass balancer calculated 4 correction masses so that the overall center of mass moves onto the rotation axis and the unbalanced mass becomes 0. As shown in this report, after balancing, the X and Y center of mass offsets become 0, which means the rotor is statically balanced. In one of the investigations using this mass balancer, I will show you a plot where you can understand that how a small mass imbalance can cause significant loading at high speeds. So in this plot, you can go through our tutorials for this mass balancer. And here you can see the green curve is the force when we have put the small mass balancing for the rotating rotor at really high speed. And the blue was the initial condition where there was some imbalance in the component. Now we move to the extended animation that supports hydrodynamic bearing pressure visualization. As Swapnil mentioned that this enhancement is no longer limited to only crankshaft bearings. So firstly, to have the hydrodynamic pressure, let us first create the HD profiles. To save our time, I will just use a single bearing right now. And we run a steady state analysis. Hope this doesn't take much time now. So before the webinar, I had tried these settings and the simulation was fast, but it is taking some time. So it is the beauty of live demonstration, I can say. So we have our simulation run. Now the enhancement is made available under the review menu. You observe that it took some time to open the dialog box because it first scans all the currently opened assemblies in the session to check if they contain the required components. The required components are either the hydrodynamic bearings. As you can see, it has detected that it contains a hydrodynamic bearing instance, or gear elements together with general gear pair contact. If the matching assemblies are found, they are listed in the model name dropdown. Next, the selected model must also contain analysis. All the available analysis are under the analysis name dropdown. I will say load data. Here you can observe that we have a rainbow of 10 different colors for hydrodynamic pressure display as well as for contact pressure. In the background, the software is creating the visual data for our better visualization. So the graphics is also updated on the fly. Let me zoom to the bearing one. Here we are looking into the pressure evolution over the time and how the bearing load develops. In the dialog box, you can adjust the max value, mean value to display, and also you can uh, use a scaling factor to improve visibility. Separate maps can be plotted for the hydrodynamic and contact pressures. Additional overlays such as the hydrodynamic force, contact, orbits are also available. This is usually the moment users realize that static plots miss part of the story. Now we move to similar animation enhancement for gears. Let us run a generic interactive run. Choosing the dyno settings. Say yes. Before we run the animation, we can change the force graphics under settings option just to have a better visibility of the force vector. Similar to the bearing, we now check for the gear pair instance. So the software has detected that this model contains a gear pair connection. In the gear pair case, again, we have 10 different scales for the Hertzian pressure and the wear indicator. This animation is slightly faster because I use smaller step size. Let me try a trick to see if I can slow down the animation speed. Uh, I'm trying to open the post processor. Hope this trick works and we have a smaller speed. Okay, this is slightly better. And we can see the pressure development. Similarly, we can plot the wear indicator. So over here, the wear indicator combines the local sliding velocity with the local Hertzian pressure. Finally, we will briefly look at the licensing improvements that have been introduced. So as Swapnil mentioned, that with this update, the licensing system has been modernized and made much more easier. The management now happens directly through the web browser, so there is no need for additional tools or setup. It also removes the dependency on Java, reducing installation and maintenance effort. On top of that, configuration now supports YAML, which makes the setup cleaner and easier to manage. Overall, the whole process becomes simpler to deploy, easier to maintain, and more user-friendly. That brings me to the end of today's demonstration. We have covered the simulation improvements, visualization enhancements, and the licensing updates across the release. Thank you for joining today. If you would like to explore these features further, detailed tutorials and examples are available in our help documentation, as I showed during the demo. And with that, we open the floor for any questions you may have. For any question, any virtual dynamics related support, feel free to reach out to us by email. Also connect with us on LinkedIn to stay updated with the latest news.
Thank you for the demonstration, Prashant. I will actually leave the screen to you because there was a question regarding, when we were plotting the gear signal and showing when the synchronizer started, there was a question of why was there a big gap? Do you have the plot still open? Can you go back there?
Yes, I will open. You are talking about this plot or the first one?
The previous plot, the first one.
Okay. Yeah.
Yes, exactly. So this gap, right? So maybe if you just show this delay parameter in the dialog box, the one which is causing this, that the actual synchronization takes place later. If you just go to the dialog box
Gear.
of the
Okay.
of the gear synchronizer, do you have it open?
Just a second. I will open the model.
Yeah, while you open it, I can just say this. So this is just another, let's say, play parameter, right? For different reasons, if you want to just check the effects of different engagement if they happen at different point of time or something, and that's why this parameter delay under the friction clutch, right, Prashant? What is 100 for Prashant right now? Exactly. Yeah.
Yes.
So
Yes.
this was the reason of the delay.
Right. So the user can adapt this value as per his current investigation.
Correct. And once again, I invite people to write in their questions on the dialog box. We had some questions already during the presentation. And let me start from The very first one, and I completely understand it's a justified question. Why is this version called 2025.2? What is this numbering? Um, we basically base our releases on every major release of Atoms. And after a major release of Atoms comes, technically we do a code freeze. We do all the checking, regression analysis, regression tests, and it takes us a few weeks to get the major release of virtual dynamics. And the release cycle for MSc Adams is summer winter. But this time, instead of release in December, it was delayed to sometime in March, which led to our delay for sometime end of April, beginning of May. But in order not to cause confusions, we use the same numbering as Adams. And yeah, there's nothing, we can of course go for a different numbering scheme, but then you always need to, when you're installing Adams and Virtual Dynamics separately, you always have to basically look up which version is compatible with which one, and we don't want to cause that confusion. That's the reason. I'll go to the next question. Is the gear signal meant for triggering the gear shift in the model? How can it be controlled? Yes, the gear signal, if I understand the question correctly, what Prashant also showed in the plot, basically that is the control of the gear engagement of when and how it would happen. Of course, how it would happen is controlled by the parameters in the synchronizer dialog box. But when the engagement or disengagement will take place, it's controlled by this signal, and there are actually multiple ways. So you can write your own functions. You can use communicators, or you can also use variables in order to control it. So for example, if you are using Adams control, right, you have a complex control strategy from Adams control, then you can have a different subsystem of Adams control model. And using communicators, you can always just pass on the information of the gear signal uh, to the gearbox model in the assembly. But there are multiple ways, and there are also you can just hard code it in time, very simple, or you can also write complex functions or use variables. I hope that answers the question. Which is the next. Do I need additional RBE and interacting nodes for the mass balancer? I think interface nodes is what is being meant over here. So the mass balancer, let us put it this way, yes and no. Not the greatest answer, right? But if you have RBEs, if you can pre-plan that, okay, these are my balancing positions, and you are able to, create a very small RB element which is connected to 4, 6, or 8 nodes, it's helpful, but it is not necessary, because in the end, in a realistic case, the balancer is adding very small loads, so very small masses, which means that if you are going to select any local surface node on the body or the flexible body, it is not really going to create a significant excitation loading. But of course, that said, we would always recommend you to select non-critical locations for positioning this balancing, additional balancing masses. And interface nodes. So again, first of all, RB is not compulsory. Even if you have RB, you definitely do not need the additional constraints, because you are not really interested in looking at the local dynamics of that mass. So interface node is not necessary. The next question again on the mass balancer. Does the mass balancer make decisions for me, and would it be why would it be typically recommended? I mean, make decisions for you in a way, yes. So the mass balancer is only for 100% balancing, right? It's not. So if you say that you want to balance, uh, basically the center of gravity, you want it to be at 0 and 0 on the rotational axis. You say you want to balance it, then the mass balancer makes the decision for you. It finds out the perfect combination of masses with the aim of keeping the additional masses as to be minimal. And why would it be typically recommended is because, as mentioned earlier, discretization, when you create FE mesh, it leads to imbalance. And I think Prashant also showed this example of the forces which were going up to significant tens of newtons in the bearing. If you look at the position of the center of gravity, uh, it's it's really small, maybe order of microns, some dozens of microns. So it looks really small, but it can lead to significant loads. And if you are, where would be typically recommended is if you are working with any critical component where you know that during the production, right, the crankshaft or the rotor of the e-motor or the camshaft, during the production, they are actually controlled for their balancing, and additional weight is added or sometimes material is removed to get better balancing. So if you're working with a component which even in reality is uh, balanced after the production, right, due to then you should also be doing the same in your model here. uh, there are some questions in review, Prashant. I will just publish them. I will let you answer this one. The question is, we use different versions in the team. So I think they mean the different versions of virtual dynamics are being used in the team. How do they
Okay.
manage their server license? Because I think because they are forced to use the new license manager for the latest release, but they want to use different versions of virtual dynamics in the team. I think you can answer this one.
Oh, yes. Thanks for bringing up this up because I missed to mention about this part that with the latest Virtual Dynamics release, you will have to upgrade it to the newer version, uh, the 6.0.6. But the good news is that all the license files what we have already issued remain fully compatible with the new version, and the updated license manager also continues to support the older Virtual Dynamics releases. So once you upgrade it to the latest 6.0.6, you will be able to get the benefits of the latest technology, and it will help you on your administrative efforts as well to maintain the licensing manager. And yet you can still use different versions from past as well as the latest version. I hope this answers your query.
Yes, and if I may add, so the latest this license manager, the executable is available on the download portal along with the release files, correct?
Yes, yes, we have
Yes,
uploaded the
so
latest version.
exactly.
And also it is part of the installation package of the version you are using, the latest version download package.
Yes, I think that was quite clear for me. I will go to the next question. We have two more questions, 4 more minutes, but I'm happy to answer any more questions if they come in. The next one is, how are these four masses positioned along the length of the shaft and connected to the flexible body? Does it work only when you have four RBs along the length of the shaft? So the position of the masses is actually user input. So then, of course, we recommend that you select strategically the different position, but yes, 4 masses are required. The way it has been created, it cannot be done with 3 masses. It will need 4 masses for doing the optimal balancing. Uh, so that's one part of the question. It does not have to be along the length of the shaft. You can select strategically positions, but of course, if you select all points in the same quadrant and on the same side, then it becomes very difficult for the balancer to find a proper balance by adding masses, right? So you need to strategically spread out the location of this mass points. And yes, it works only, you do not need 4 RBEs, but you need 4 locations. So how were they connected to the flexible body? In this case, um, we used RBEs, yes, and we knew where the location of the RBE interface node is, right? So it's not there were no constraint modes assigned to it, but we knew where it was, and the same locations were given as input in the dialog box. And then similar to whenever you replace or whenever you create a flexible body, you get this report file which says in the first column the location of the expected node, second column the location of the FE node, and the distance between them. And then it does creates an automatic connection. I hope this is also clear enough. Prashant, I have been scrolling through the questions. If you don't mind, also, can you go through the questions to see if I have missed anything? Otherwise, this one is for me, the last question for right now, unless something new comes in the review. Even if I'm not modeling gear shifts, is it still worth including a synchronizer in the model? It's a very interesting question. We have also thought about it. So this synchronizer does not add any additional inertia to your model, which means that it is still expected that if you're using this analytical gear synchronizer, that the inertia of this entire mechanism, the synchronizing mesh and the ring as well as the gear itself, is all already provided in the gear inertia. So no, that way it is not required. What this does is it creates an additional. So if you are thinking of the force transfer in your system, right? Instead of going from the gear to the shaft, especially if you are just doing a fixed joint, in this case, it goes through an additional spring damper element. Now, what are the, so you are basically having, let's say, the contact of the gear, which is a spring damper element in some sense, then the gear body itself, and then this three. You have 3 stiffnesses in parallel. And now it is for you to decide whether this is important for you. But in other sense, it can also be avoided by simply not using a fixed joint between the gear and the shaft, or rather just define a spring damper element over there, which is also possible. So maybe it is not required if you are modeling already your gearbox smartly. I hope that answers the question, but of course we are always available for any further questions, any further clarifications. Prashant, do you think, is there any particular question that I missed?
Uh, I guess we have covered all the questions being asked. I also don't see a new one.
That's great. Then we can conclude almost on time, 1 minute over time. And I thank all of you for your time and interest today. We hope you are excited as us to use and try the new version, and we look forward to your feedback on the same. Thank you once again for your participation and have a nice day.
Thank you.
Thank you, Prashant. Thank you, Adrian.
Thank you, everyone.